Engineers once poured enough concrete to circle the entire Earth twice, and if they'd done it the normal way, sitting there cooling and hardening naturally under its own weight, it wouldn't have finished setting until sometime in the next century. This is the Hoover Dam, and the way they actually solved that problem is one of the strangest, most undertold fixes in engineering history. A fix that's still sitting inside the dam right now, sealed away, invisible from the outside, doing nothing anymore except being the reason this thing has survived for almost 100 years without a single major structural failure. Act 1. The problem. In the early 1900s, the Colorado River was both a lifeline and a threat. It watered farmland across 7 states, but it also flooded without warning, and in dry years it left those same farms with nothing at all. The Southwest needed 2 things badly: flood control and a reliable water supply, and both pointed to the same solution: block the river completely with something massive enough to actually hold it back. So in 1931, construction began on what would become the largest concrete structure ever built at the time. Over 3.25 million cubic yards of concrete, enough to build a 2-lane highway stretching from San Francisco to New York and most of the way back. Thousands of workers arrived at a dry, brutal desert canyon during the middle of the Great Depression, drawn by steady paychecks on a project most people back home assumed was too ambitious to actually finish. And that's exactly where the first impossible problem showed up. Concrete doesn't just harden, it cures, releasing heat as a chemical reaction plays out inside it, and a mass this size generates an enormous amount of that heat as it sets. Left alone, a block of concrete this thick wouldn't finish cooling and curing for well over a century. The outside would harden fast in the open air. The inside would stay hot, expanding against the already hardened shell, slowly cracking the entire structure from within as it tried to cool down over generations nobody building it would live to see. They didn't have generations. They had about 2 years before the dam needed to start holding back an entire river. Act 2. The fix. The solution engineers landed on sounds almost too simple for a problem this enormous. They cooled the dam from the inside, the same way you'd run a refrigerator line through solid stone. Workers embedded more than 582 miles of steel pipe directly into the concrete as it was poured, section by section, layer by layer, so no single pour was ever more than a few feet thick before the next cooling line went in. Then they pumped ice-cold river water, and later refrigerated water from an on-site ammonia refrigeration plant, one of the largest of its kind ever built anywhere in the world, directly through that pipe network, physically pulling the heat out of the concrete from the inside as it cured. It worked. What should have taken over a century to cool naturally was fully cured in under 2 years. Engineers monitored the temperature constantly, adjusting the flow of cold water through different sections depending on how fast each block was curing, treating the entire dam less like a single pour and more like thousands of individually managed concrete blocks working together. Once the cooling was finished, engineers pumped grout into those same pipes to seal them permanently inside the dam for good. That means the entire cooling system that made this project possible is still in there today, buried inside millions of tons of concrete, doing nothing anymore except quietly holding up a structure it once saved from tearing itself apart from the inside out. Act 3. But cooling the concrete only mattered if the dam had something solid enough underneath it to actually hold that weight for a century without shifting, cracking, or settling unevenly the way so many other massive structures eventually do. And solving that problem meant fighting something almost as unpredictable as the heat itself. Bare canyon bedrock nobody had ever fully mapped. That fight is where this story ends. First, we need to understand why solid ground is never quite as solid as it sounds, and there's no better way to see that than through 2 very different builds that were forced to learn the exact same lesson decades apart on opposite sides of the country. Act 4. The Golden Gate's invisible enemy. 5 years before Hoover was finished, engineers 1,000 miles away were fighting a version of the same fight, just against a different invisible force. The Golden Gate Strait isn't just wide, it's one of the most hostile stretches of water on the American coast. With fog rolling in almost daily and winds funneling through the gap between the cliffs strong enough that naval officials had spent years insisting a bridge there was simply impossible to build safely. Chief Engineer Joseph Strauss took the job anyway, but he knew the real danger wasn't visible from a blueprint. So his team ran early wind tunnel testing to make sure the deck wouldn't twist itself apart in a storm. Testing scale models against wind speeds most engineers of the era had never bothered accounting for, a problem so poorly understood at the time that a smaller suspension bridge built years later, Tacoma Narrows, collapsed in 1940 specifically because its engineers skipped that exact step and assumed a stiff-looking design was automatically a safe one. Golden Gate opened in 1937 and is still standing today, for the same reason Hoover Dam is still standing today. Because someone went looking for the invisible failure point before it became a real one, instead of finding out the hard way after the fact, at the cost of an entire structure. Act 5. The Millennium Tower's Warning. The opposite lesson shows up in San Francisco, decades later, where a 58-story luxury tower called the Millennium Tower started sinking the very year it opened, eventually more than 18 inches into the ground, leaning enough that residents could set a marble on the lobby floor and watch it roll across the room. The cause was buried far below anyone could see it, a layer of soft, waterlogged clay under the tower's foundation, slowly compressing under the building's own weight, exactly the kind of invisible ground problem that has doomed towers, bridges, and dams alike throughout history whenever someone assumes the ground beneath them is stronger than it actually is. Engineers eventually fixed it the same way Hoover's team solved their own invisible problem decades earlier, not by fighting the symptom, but by going straight after the hidden cause. They drilled new piles more than 250 feet down, past the bad clay entirely, connecting the tower directly into solid bedrock it should have had from the very beginning. The project took years, cost tens of millions of dollars, and required drilling directly next to a fully occupied residential tower without making the tilt any worse in the process. The sinking finally stopped. The tower has since very slowly begun leaning back toward vertical. Two buildings, decades and 1,000 miles apart, both fighting a version of the same invisible enemy. One found its enemy before construction ever started. The other found it 15 years too late and spent a decade and a fortune fixing what should have been solved on day one at a cost far higher than doing it right the first time would ever have been. Act 6. Back to Hoover, the foundation fight. Which brings us back to Black Canyon in 1931, where Hoover's engineers were determined not to repeat that mistake. Before a single bucket of concrete could be poured, they had a harder problem than cooling the dam. They first had to remove the Colorado River from its own canyon entirely. Crews blasted 4 massive diversion tunnels through the canyon walls, each nearly 50 feet across, to redirect the entire river around the construction site while the dam rose out of the now dry riverbed. Then came the part that actually mattered most, clearing the canyon walls and floor all the way down to real, unweathered bedrock. Not just rock that looked solid, but rock genuinely stable enough to carry the full weight of the tallest dam on Earth at the time. Workers rappelled down the sheer canyon walls on ropes, drilling and blasting away loose rock by hand, in some of the most dangerous working conditions of any American construction project of the era. They became known as the High Scalers, dangling hundreds of feet above the canyon floor with nothing but a harness and a jackhammer, clearing away every loose boulder that could have fallen on the crews working below. Dozens of workers died over the course of the project, a cost the men on site understood clearly and accepted as the price of a job that paid steady wages during the worst economic collapse the country had ever seen. Every single section of exposed rock had to be inspected and formally approved before the first form for concrete could even go up, because if the bedrock underneath had one hidden weakness, no amount of engineering above it would have mattered at all. It was slow, brutal, unglamorous work, and it's the reason almost nobody talks about it today. The finished dam gets all the attention, and the canyon wall it stands on barely gets a mention. Act 7. The Payoff. Hoover Dam was finished in 1936, 2 full years ahead of its original schedule, standing 726 feet tall over a foundation its engineers had personally verified, section by section, before a single ton of concrete ever went above it. At the time, it was the tallest dam ever built anywhere on Earth, and it created Lake Mead, the largest reservoir in the United States, capable of holding back years of the Colorado River's flow in a single basin. Today, nearly a century later, that same concrete cooled artificially in under 2 years instead of naturally over.